You know, in the world of math, there are problems, and then there are monsters. These are equations that are so complicated, so unwieldy, they seem to basically defy any kind of solution. Well, today we're going monster hunting, and we're armed with a pretty revolutionary new weapon. So, what does a mathematical monster like this even look like? Well, you might want to brace yourself. It is not for the faint of heart. Okay, here it is, an 18th degree polynomial. I mean, just look at this thing. It's got 19 terms, coefficients that are absolutely massive. It's just sprawling all over the page. And the challenge? Find the value of x that makes this entire beast of an equation equal 0. It's a monumental task, to say the least.
Now, if we're going to solve this, we first have to understand why this thing is considered such a monster in the first place. The real troublemaker here is this number, 18. That's the highest power, or what we call the degree, of the polynomial. Now, you probably remember solving x-squared equations back in high school, right? But here's the thing. Once you get past a degree of 4, finding a nice, clean, exact formula for the general case becomes, well, famously impossible. It's been proven, and we are way, way past 4 here.
And that's exactly where the old-school methods, the classical algebraic tools, they run into a brick wall. This brings us to a really important difference in what solving can mean. See, we can ask a computer for an answer, and it'll give us what's called a numerical approximation. It's a number that's incredibly close, but it's not perfect. It's always going to have tiny little rounding errors. But for a mathematician, the real holy grail, that's the symbolic solution. A perfectly exact expression, no rounding, no close enough. It's the pure, elegant truth of the equation. And this is where things get really interesting. The author of the method we're looking at makes this incredibly bold claim. They say their approach sidesteps these classical limits, even challenging a famous theorem by a mathematician named Abel, which basically sets the rules for what's considered solvable. That's a huge deal. So what is this new approach? It's called Ezouidi's theorem, and it's specifically designed to do what a lot of people thought couldn't be done. Find that perfect, exact, symbolic answer. So, to put it simply, the theorem creates a kind of systematic recipe. Instead of just guessing or approximating, it transforms the original monster polynomial into a new form that we can solve directly and, most importantly, precisely. It's like finding a hidden structure inside all that chaos. And the method itself follows this really clear 3-step game plan. First, you translate the monster equation into a new kind of symbolic language. Second, you use a special repeating process, what's called a recursive process, to calculate a new set of key numbers. And finally, you use those new numbers to find the exact answer. It's a plan of attack. All right, this is it. This is where the magic happens. We're about to apply this theorem to our monster and see if we can actually crack its code. So, the process generates 18 of these new symbolic coefficients, which we'll just call S0 through S17. Each one of these is calculated using a pretty complex formula based on the numbers in our original monster equation. Think of these as the secret keys that are going to unlock the whole puzzle. Okay, let's fire up the process. We compute that first coefficient, S0, plugging in all those massive numbers, and after all that crunching, the result is exactly 0. Okay, 1 down, 17 to go. Now for the next one, sum 1. The formula gets even more complicated this time, and yet the answer is the same. Perfectly 0. Wait a second, is that a coincidence? Let's check one more. So we calculate S2. The computation is even more intense, but again, the answer simplifies all the way down, 0. Okay, this is definitely not a coincidence. Something is happening here. And this is the incredible result. After all 18 of those complex calculations are done, it turns out that every single one of the new coefficients, from S0 all the way up to S17, is 0. All of that initial complexity, all those huge numbers, they just perfectly cancel each other out. They vanish. So what does this all mean? If all our new secret keys are 0, what happens to our monster equation? This. This is the payoff. Let's just take one last look at where we started, this absolute beast of an equation with all 19 of its terms. Because every single one of those S coefficients turned out to be 0, they effectively wipe out all of the terms in the middle of the polynomial. And what are we left with? The entire equation just collapses into this shockingly simple form. x to the power of 18 equals 0. And the solution to that is just beautiful. I mean, what's the only number you can raise to the 18th power and get 0? It's 0 itself. This means our monster equation has just one single solution, x equals 0. It's what mathematicians call a root with a multiplicity of 18, which is a fancy way of saying it's the same answer, just repeated 18 times. The monster, it was just a really, really complicated disguise for something incredibly simple.
And this just hammers home the whole point of the theorem. It didn't give us a pretty good answer. It delivered the precise, perfect symbolic root. It took a problem that would totally stump traditional methods and revealed its true, exact nature.
And that leaves us with this really fascinating question, right? We've just watched a mathematical monster get completely tamed just by looking at it from a new angle. It really makes you wonder, what other impossible problems out there aren't really impossible at all? They're just waiting for the right perspective to reveal their simple, elegant solution.